Time to look at an old differential equations exam. So this is Math 267, which is just differential equations, our second exam. Now that means it's about systems, matrices, so all sorts of fun things. If you love linear algebra, you'll love this exam. And if you don't love linear algebra, I hope you'll still love this exam because there's some fun problems on there. 6 problems, and let's go ahead and get going. Of course, the first thing we always do is we put our name on things so that we will get the credit. So for us, we're going to put answers because that's what we're after. We're after the answers. Let's get going. Number 1, use any method to find the general form for x and y for the following system. X prime equals 7x minus 2y, y prime equals 5y minus 4x. Now when they say any method, we could do things like substitution, elimination, or turn into matrices. And matrices is my preferred go-to because we have a lot of tools to help us succeed. But I want to point something out here. They did something to us. And of course, you know, they're very wily, these test writers. Notice 7x minus 2y, yeah. 5y minus 4x. They changed the order. So if you weren't paying attention, you might not notice that. Now what do I mean here? Well, normally we would have written as minus 4x plus 5y. So in matrices, this would be written as x prime equals, and you write your coefficients, 7 minus 2 minus 4 plus 5 times x. All right, so there we go. That's our system there. And so if we hadn't been careful, we'd run it as 5 and negative 4. Now it turns out, and this is them being either devious or mean or whatever you want to call it, if you swap them, you will get the wrong answer, but it'll be a nice looking wrong answer. So, you know, you would have gotten still a lot of points. I just want to tell you that ahead of time. All right, so our first problem with matrices. Now, what do? Well, we've got to find eigenvalues, eigenvectors, and then put everything together. And because we're after the general form, right? So we're not after a specific solution, just a general form. Okay, so first off, let's do our eigenvalues. Okay, so for that, remember what we're doing is we're going to take the determinant of a minus lambda I. Now, this is our a. So what we're doing here is we have our determinant of 7 minus lambda, minus 2, minus 4, and 5 minus lambda. Well, that's 7 minus lambda times 5 minus lambda, subtract negative 4 times negative 2. Right, down the diagonal, subtract up the other diagonal. Well, multiplying this out, that's 35. Minus 7 lambda minus 5 lambda makes minus 12 lambda. Then minus lambda times minus lambda is a lambda squared. Minus times minus 4 times minus 2, 3 minuses end up with 1 minus at the end, and that's minus 8. So we have lambda squared minus 12 lambda, and here 35 subtract 8 is 27. Okay, so can we think of two numbers that multiply to 27, add to 12? Well, not a lot of things multiply to 27 because 27 is 3 times 3 times 3. So we have 1 times 27 or 3 times 9, but 3 times 9 looks great. So this would be lambda minus 3 and lambda minus 9. Set that equal to 0. And we get that our eigenvalues are going to be 3 and 9, right? Because lambda minus 3 equals 0 is 3. Lambda minus 9 equals 0 is 9. All right, good. Now that's our eigenvalues. Now we have to do eigenvectors. So how do we do that? Well, actually, once you have eigenvalues, it's not too bad. So suppose we have our eigenvalue for 3. So I'm going to look at this same a minus lambda I, and I'm going to subtract lambda equals 3. So 7 minus 3 is 4, and then minus 2, and minus 4, and then 5 minus 3 is 2. And now, the thing that you have to figure out is what can you put here to get out 0, 0? And there's lots of things, except don't use 0, 0. Now, you can stare at it for a second. One thing you can do is if you see a row, you should just say, look, reverse the row and flip the sign on a single entry. And so, for instance, 2, 4. That would work. And right, because you get 8 minus 8. And minus 8 plus 8. So we say, oh, okay, so we can use 2, 4. Or we can say, look, any multiple of that works. Okay, so how about 1, 2? That's a little bit cleaner. What about lambda equals 9? Well, okay, now subtract 9. 7 minus 9 is minus 2, minus 2, minus 4, minus 4. And now, what can you put there so we get 0, 0? Well, you can swap the entries, it doesn't really matter, so they're the same, and just change the sign on one of them. So, for instance, 2 minus 2 works. Minus 4 plus 4, minus 8 plus 8. And of course, we can scale. Say, oh, we could use 1 minus 1. So, we have our eigenvalues and our eigenvectors. So in terms of this as a matrix, we say, aha, our x looks like some constant, I'll use the letter b because we used a for the matrix, times the eigenvector 1, 2, e to the eigenvalue t, plus some other constant c, and eigenvector 1 minus 1, e to the eigenvalue 9t. And now you're like, aha, we're done, right? 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 No. No, we're not done. Now, what's our problem? The problem is we're the ones who introduced the matrix notation. The problem did not do that. We did that. So how do we undo it? Well, and the answer is we say, oh, well, what we do is we just realize, what does this x represent? This x, and of course you can't tell by the way I write, this is a vector x, not the same as this function x. So what we really have is x and y. So what we do is we now grab the first row, that's the x, and the second row is the y. So x would look like some b e to the 3t plus c e to the 9t, and y would look like 2b e to the 3t minus c e to the 9t. So just go along the top row. b times 1 times e to the 3t, c times 1 times e to the 9t, b, bottom row, b 2 e to the 3t, c minus 1 e to the 9t. And that's our answer. Of course, there's other answers as well. Now, you might say, oh, hey, Steve, you oftentimes talking about how constants can absorb constants, right? So why do we write 2 times b here? Can't we just write that as b? Well, we could, but the thing is, these b's are related. So if I change this one here, I have to change that one there. So it's not the case that I can arbitrarily absorb constants. It's that I have to arbitrarily absorb constants in the same way. And so when you have multiple equations, you have to say, well, there will be other numbers showing up in the general solution. So that's okay. That's all right. But there we go. A nice warm-up. And more fun problems lie ahead. Number 2. Find a differential equation only involving y, given that x double prime plus 2x plus 2y prime equals 0, x prime plus 3x plus y double prime is e to the 2t. And you do not need to solve the differential equation. One of our favorite phrases, do not need to solve. Okay, so what's going on here? Well, we have a system of 2 equations, which involves second derivative, so it's a second order system of 2 equations. And we're trying to get down to 1 equation, only for y. So this is about elimination. And we say, okay, So we're going to do elimination on this problem. And in particular, this is a variant of Cramer's rule, right? So let's first off work on rewriting. So for instance, this is going to become, using our d notation, d squared x plus 2, whoops, not 2d, 2x plus 2dy equals 0. And then dx plus 3x plus d squared y is e to the 2t. Or, if you like, in matrices, this becomes, see, in here you can factor out the x, so it's really d squared plus 2. Then it's d plus 3. And then 2 times d squared, and times xy equals 0 e to the 2t. All right, so what happens? We're after y, and because it tells us we're after y. And so we're after that part right there. So we say, okay, so here's the lovely rule. So what we're going to do is we're going to take our determinant of our original expression, d squared plus 2, 2d, d plus 3, d squared, and times y. And that's going to be the same as the determinant when we replace the second column by 0 e to 2t. Now, why the second column? Well, the first column is associated with x. The second column is associated with y. So we're replacing the column associated with y. So again, that's d squared plus 2, d plus 3, 0 e to the 2t. All right. Well, most of the rest of this is just working it out. So we have d squared plus 2 times d squared. That makes, well, we'll go ahead and do it a little slowly. We're not in a rush. We can savor our problems, right? And subtract d plus 3, 2d times y is d squared plus d e to the 2t, and subtract 0, because, well, it's 0 times anything is 0. Okay, so that would be d to the 4th plus 2d squared, and here you have minus 2d squared minus 6d, because you multiply through, and we get some cancellation, which is good. So d to the 4th times y is the 4th derivative of y. We can go ahead and write it that way if we want. Minus 6d times y, so that's minus 6 y prime, is equal to. Now here, if I take two derivatives of e to the 2t, I'll get 2 coming down twice. So the first derivative brings a 2, the second derivative brings a 2. That's 4 e to the 2t. Then I'm going to add a derivative of e to the 2t, which is 2 e to the 2t. 4 e to the 2t plus 2 e to the 2t makes 6 e to the 2t. So we get 6 e to the 2t. And so that's a differential equation that involves y, and only involves y, not involving x. And so that's our answer. And we're done. Cool, cool. And, well, that wasn't so bad, right? As long as you know the right tool and the right technique, the problems have a tendency to work themselves out. It's the best kind of problems, the problems that work themselves. All right, well, 2 down. We're already a third of the way through. Amazing. Let's keep going. Number 3, find a fundamental matrix of solutions for x prime equals 8 minus 1, 4, 12, x. All right, fundamental matrix. Well, first thing we should do is figure out the eigenvalues. And let's see what they are. Okay, so we have 8 minus 1. So we're going to do 8 minus lambda minus 1, 4, 12 minus lambda. And if we multiply this out, this becomes 8 minus lambda, 12 minus lambda, subtract. 4 times minus 1. Okay, so that would be 96. And then we have minus 8 lambda, minus 12 lambda, that's minus 20 lambda. And then plus lambda squared, and plus 4. Well, that's lambda squared minus 20 lambda plus 100. Do we know two numbers that multiply to 100 add to 20? Yes, we do. That makes it lambda plus 10. Lambda minus 10 quantity squared, because there's minus 20, so that's why it's minus. And so we say, aha, our eigenvalues are 10 and 10. And now we're like, yes! Yes! This is awesome! Woo! Right? Because we are asked to find a fundamental matrix for repeated eigenvalues. And we're just like, high fives, everybody! Let's do this! Why are we so excited? Have we had too much coffee? Maybe, but probably because we're like, oh, it turns out that fundamental matrices for repeated eigenvalues are beautiful. So how does it work? So if you have a 2 by 2 matrix, repeated eigenvalues, then the fundamental matrix, well, I said the fundamental matrix. Really, there's a fundamental matrix, but I like the fundamental matrix. You can use e to the at as your fundamental matrix for x prime equals ax. And repeated eigenvalues, it turns out it's e to the lambda t times I plus a minus lambda I, times t. So there we go. That is nice. Okay, now you might say, wait, e to the at, is that a fundamental matrix? It is. It's sort of the best fundamental matrix. So we say, okay, so in our case, what do we have? Well, we have lambda is 10. So this becomes e to the 10 times t times the identity, 1, 0, 0, 1, plus a minus lambda I. So in this case, you take your matrix, subtract 10. So that would be minus 2, minus 1, 4, 2 times t. And all right, so that's putting it together, e to the 10t times 1 minus 2t minus t, 4t, and 1 plus 2t. And we're done. That's it. That's it. That's all you need. As long as you remember e to the at is a fundamental matrix and how to handle it with repeated roots. Now you might be saying, well, what if I forgot that? Oh, okay. Well, no problem. You can still do this, right? So how do you do it? Well, it turns out, we'll go ahead and do it. And, all right. So what do? Well, you say, okay, eigenvalues are 10, but our matrix is not going to have enough eigenvectors. But we still start by saying, well, what's an eigenvector? So we have minus 2, minus 1, 4, 2, times something has to equal 0, 0. All right, well, what's the something? Well, you can swap the entries and just flip the sign on one of them. So for example, 1 minus 2 works, and you'll see we get minus 2 plus 2, 4 minus 4. And so we say, aha, 1 minus 2 is our eigenvector. Now, the next thing, we need to find something so that when we multiply, we're going to get our eigenvector, 1 minus 2. And we look at it and say, well, there's a couple of options, and there should be. One easy thing is it's almost a second column, just the sign is wrong. And so we say, okay, what about 0 minus 1? Does that work? And you see, okay, 0 plus 1, good. 0 minus 2, yeah, that's good. So if we call this vector v, we call this vector u, then our solutions have the following form. The first one has the form of v times e to the lambda t. The second one has the form t times v plus u e to the lambda t. So essentially, we're bumping, but the bumping has a little correction, and that's the thing that we had to find. So for our case, what do we get? Well, we have our two solutions are going to be 1 minus 2 e to the 10t, and then our second solution is going to look like t, 1 minus 2, plus 0 minus 1 e to the 10t. Now, how does that get us to our fundamental matrix? Well, we have to remember what the fundamental matrix is. Our fundamental matrix is we pack the columns with solutions. So we need two solutions because there will be two columns. So we say, okay, our fundamental matrix, everything involves an e to the 10t, so we can go ahead and pull that out. And our first column would be 1 minus 2. And our second column, well, that would be t plus 0 and minus 2t minus 1. And there's our answer for a fundamental matrix. Now, I want to be careful here because it does say a fundamental matrix. Fundamental matrices are not unique, but there's a best one, which is the e to the at. So we were able to say, okay, these are both correct answers. And which one do you like? Well, it's not that we don't like one over the other. They're both correct. It's just if you understand the tools, and you can get a shortcut, and why not? Why not get a shortcut? But if you don't want a shortcut, yeah, sure, do the work. You'll get a right answer, and life is good. Now you might say, well, how did you get between these two? And the correct answer is you can get from here to there by, if you take this phi of t, multiplied by phi 0 inverse, you will get this expression as well. But for now, we're happy, we're satisfied. Life is good, and let's keep moving on. Number 4, solve the initial value problem. X prime equals 2, 1, minus 4, 2x, with x of 0 equals 2, 2. All right, so we start with the same thing. There's a process, right? We're going to find our eigenvalues, and once we have our eigenvalues, we start making decisions about where to go. So it depends on whether the eigenvalues are repeated, or whether they're distinct real, or whether they're complex as to where we go. But we always start with finding the eigenvalues. And so we're going to get really good at that. And if you haven't gotten really good at it, well, don't worry. You still have time. And with time, you'll get better. So this becomes taking the a minus lambda I, taking that determinant, 2 minus lambda times 2 minus lambda, subtract negative 4 times 1. Well, that's going to give us 4. Then minus 2 lambda, so that's minus 4 lambda. And then plus lambda squared, and plus 4. So this is lambda squared minus 4 lambda plus 8. Now, we have to set that equal to 0. Does that factor? I don't see it. Doesn't mean it doesn't. It just means I don't see it. There's a difference between I don't see it and it doesn't, right? Because sometimes you're like, dang it, I missed something. So what can we do? Well, there's two options. One is complete the square, and the other is quadratic formula. Why not do the quadratic formula? We should. An oldie but a goodie. It's a classic, right? So we take negative b plus minus the square root b squared minus 4ac all over 2a. And we already see that inside that square root, negatives. This is going to get a little bit complex. That's all right. We're okay. We're not going to panic, at least not yet. Maybe we'll panic later. So 4 over 2 is 2, plus minus. Square root, well, this is going to become negative 16 on the inside. Square root of negative 16 would be 4i. Divide by 2, makes 2i. All right, so 2 plus minus 2i. All right, great. Well, okay, now what? Well, now we need to find ourselves an eigenvector. And we actually just need to find one. And because with just one eigenvector, we can extract both solutions. It's one of the cool things about complex. It's because of the nature of complex numbers, the fact that things come in conjugate pairs, you know, that plus minus I, it really says, oh, you actually have a lot of power even if all you have is one side of it, because you have that second side as a freebie. Okay, well, so what happens next? So we're going to find a eigenvector, just one. And we have to make sure we do it with just a eigenvalue. We have to keep track of which eigenvalue and eigenvector is being used. So in our case, let's choose 2 plus 2i. Again, it doesn't matter which eigenvalue you use, but make sure that once you commit, you're consistent. And I always like the plus. I am an optimist. I like to see the positives. So we're going to take our same matrix, but now we put in 2 plus 2i. So what do we have? We have 2 subtract 2 plus 2i would make it minus 2i, and a 1, and a minus 4, and a minus 2i. And we need something, so we get 0, 0. Well, what does it? So here, the great thing is for 2 by 2, you don't have to think hard. What you do is pick a row. I'll pick the top row because it looks like nicer numbers. And you're going to read it sort of backwards, right? So I would, instead of putting 2i and 1, or minus 2i and 1, I'm going to put 1 and minus 2i. And then we're going to flip one sign. So in other words, one of them is going to go from positive to negative. So I would say the easiest thing would be 1 and then 2i. Okay, so what have we done? We essentially wrote it backwards, and then we flipped the sign on one entry. You can check, right? Minus 2i plus 2i, 0. Minus 4 minus 4i squared is plus 4, 0. Great. It works. Wow, that's fabulous. Okay, so here is our eigenvector, and it's pretty clean as far as eigenvectors go. Now, how do we extract our solutions? Well, the way we extract is to say we're going to pull our eigenvector apart, and so we have our 1, 0, and our I, 0, 2. So in other words, the real pieces, the imaginary pieces. And then we're going to multiply it by e to the 2 plus 2it. But that becomes e to the 2t times cosine 2t, and then plus I e to the 2t sine of 2t. So of course, because they're both 2, it's like, where did the 2's come from? So the exponential 2 comes from the real part. The cosine sine 2 comes from the imaginary part. And multiply and group. Are you real or are you complex? So we get solution 1. Let's have that one be the real one. That would be e to the 2t cosine 2t times 1, 0. And then we multiply the imaginary pieces together, remembering that I squared is negative 1. So subtract e to the 2t sine 2t, 0, 2, giving us the function e to the 2t cosine 2t minus e to the 2t sine 2t. And there's a 2 I forgot. There we go. Ha ha ha. We got that too. All right. Good. That's solution 1. Solution 2, okay, similar, but now we're gathering the imaginary part. So we have these pieces. So that's e to the 2t sine 2t times 1, 0. And then we're going to add the other pieces. E to the 2t cosine 2t, 0, 2. Which gives us the following. So that's going to be e to the 2t sine of 2t, and then 2 e to the 2t cosine of 2t. All right, so what's our general solution? Our general solution, our x, looks like some constant a times our first solution. And we just, in some sense, these aren't really too bad. There's just a lot of writing whenever you have complex numbers. And then some constant b times our second solution. Now, if you're watching this at double speed, you're like, wow, it's not bad at all, Steve. Well, yeah, that's because it's double speed, right? And I almost sound normal, so I've been told. Okay, are we done? No, but we're so close, right? So what's the next thing for us to do? Well, the next thing, the last thing, is to say, hey, we have an initial value problem. And how do we know it's an initial value problem? It says it. That's a pretty good clue. And there's some initial values here. So we say, well, we know that x of 0 is 2, 2. Well, so we plug in 0. Here, wherever we see a sine of 0, you get 0. Cosine of 0 and e of 0 are both 1. So that's 1, 0. Plus b. And again, sine of 0 is 0. Cosine of 0 and e of 0 are 1. So you get 0, 2. So we see that 2 is a and 2b. So we have to solve the system of equations a equals 2 and 2b equals 2. Well, these are actually really easy to solve. And in particular, we get that a equals 2 and b equals 1. So finally, we just plug in our values for a and b. So we get that x is equal to 2 times e to the 2t cosine of 2t minus 2 e to the 2t sine of 2t plus 1 times e to the 2t sine of 2t and 2 e to the 2t cosine 2t. And if we wanted to, we can put them together into a single vector. We don't have to. This is a great answer. If you like this answer, stop here. Full points. Life is good. But if you say, I want a single vector, no problem. That's great too. So we have 2 e to the 2t cosine of 2t plus e to the 2t sine of 2t. And then down, minus 4 e to the 2t sine of 2t plus 2 e to the 2t cosine of 2t. And there we go. Our answer. We're done. Now, it's possible you'll see some complex eigenvalues, because remember, there's really kind of 3 cases, and we've already seen them. Distinct, repeated, and complex. And so you want to make sure you know how to handle all of them. And so that's all right. Only 3 cases, right? We can do that. We can learn 3 things. And we can even remember 3 things for at least an hour. And so we'll be all right. But there we go. Number 4. What a problem. 2 left, right? So let's keep going. Number 5. There are 2 well-mixing tanks of sugar water. You know, people said, wait, why sugar? Well, students were feeling a little bit salty after all these mixing problems. So we said, well, let's have them leave the test feeling a little bit sweet. So we turned it to sugar. So anyways, we have these well-mixing tanks of sugar water set up as indicated in the diagram below. Ooh, pictures. I like pictures. And the values for A, B, and C are not given, but can be derived using the diagram and some of the following information. Now, when it says A, B, C, we say that there are 3 pieces of information here. All right, so let's start with part A, well, I shouldn't say part A, the first bullet point. The amount of fluid in each tank remains constant, and all rates and concentrations, including A, B, C, are constant. Now that says nothing's going up, nothing's going down. Everything remains the same. So that says inflow has to equal outflow. Now just that is enough for us to figure things out here. So take a look. Our inflow is 20 gallons, right? 10 and 10. And then when I say inflow to the system. So if 20 gallons come in, how many gallons have to go out? It has to be the same, because otherwise water levels would have to change. So we have 20 coming in, 20 going out, but that's 20 has to be 15 plus C. So C has to be 5. That was pretty simple. But we can also do the same thing here, right? Pick a tank, doesn't matter which tank you pick. Look at the inflow of either tank. Well, coming in is 10 plus A. Going out is 30. So in has to equal out. So 10 plus A equals 30. What is A? 20. All right. Well, gosh, we're doing great. And you can verify it works here, right? Because look, what's the inflow? 25. What's the outflow? 25. Okay. So we've already found 2 of A, B, and C, and we've only used 1 bullet point. The second bullet point. In the long run, the amount of sugar in tank 2 goes to 400 ounces. Huh. We'll come back to that one. The third bullet point. Initially, tank 1 has 700 ounces of sugar, and tank 2 has 120 ounces of sugar. All right. Let x1 equal x1 of t and x2 equal x2 of t be the amount of sugar in the tank, in each tank at time t. Set up in matrix form the non-homogeneous system of differential equations with initial conditions corresponding to this problem. Okay. Wow. It's all about the setup. Notice the hint. You do not, our favorite phrase, do not need to solve this problem. And then it says, to help find some of the missing information, we do need help with finding B here. Use that as t goes to infinity, x1 prime goes to 0, x2 prime goes to 0, and x1 has to approach something. Okay, well, let's see if that helps us figure this out. All right, so what is our situation here? Well, our situation is we have to look at each tank individually. And we just remember in, subtract out. So let's start with tank 1. So this is our x1. Tank 2 is our x2. So when I look at tank 1, if I want to know the rate of change for tank 1, well, I say, how much comes in? Well, there's nothing coming in here because it's pure water. There's no sugar at all. So there's 0 from that source. On the other hand, I am getting some of tank 2's sugar. Well, how much? Well, there's 20 out of the 100 gallons. So that's 1/5 of tank 2 is being put into tank 1. So I'm going to get 1/5 of the sugar from tank 2 is going to move out into tank 1, right? 20 over 100 coming in. That's the in. How much is leaving? Well, we're going to subtract. Well, we're losing 30 gallons. Now, it doesn't matter whether it flows out and away from the system or whether it flows into tank 2. We're still losing 30 gallons. So 30 out of 120 would make it 1/4 of the current amount in the tank. So 1/4 x1. All right, now we come to x2. What's happening there? Well, how much is coming in? 10b, right? Because I don't know what b is, but I know there's 10 gallons per minute, there's b ounces per gallon. So there's 10B flowing in. I'm also getting something from tank 1. How much from tank 1? Well, 15 of the 120 gallons. Well, how much is that? Well, 15 divided by 120 is 1 over 8. Because if you multiply 15 times 8, you get 120. So I get 1/8 of what's in tank 1. Now, how much am I losing? Well, I'm losing 5 plus 20. So I'm losing 25 out of 100 gallons. So 25 out of 100 means I'm losing 1/4 of x2. Now, we're almost done, right? Because it says set it up. And we also have initial conditions, by the way. It does say use initial conditions. And these are our initial conditions. So we'll come back to that. We're almost done, except for one little detail. The b. How do we find the b? And what haven't we used? You know, when in doubt, you're like, okay, what hasn't been used yet? And that's a good place to start looking for where to figure out the answer. They gave us this really long hint, which says, let t go to infinity. x1 prime goes to 0, x2 prime goes to 0, and x1 goes to a. And you say, oh, okay, so let's do that. So t goes to infinity. We'll have that goes to 0. And really what that means is in the long run, things stabilize. So the amount of sugar is going to converge to some value, and so it's not going up or down, it's staying level. That's what that means when we say something goes to 0. All right, so 0 equals 1/5. Well, how much does the sugar go to in tank 2? Well, that's the second bullet point. So this says x2 goes to 400. So 1/5 of 400 is 80. 1/4 of x1, well, x1 goes to something, we don't know what, so we can say 1/4 a. All right, and then we have 0, again in the long run, equals 10b. We don't know what that is, but it's a number. 1/8 x1. Well, okay, again, x1 goes to something, so 1/8 a. And then minus 1/4 x2. Well, again, x2 is going to 400, so that's going to go to minus 100. All right, well, what do we have? 2 equations, 2 unknowns. But really, what do we want? Do we need A? No. We actually don't need to know A. What do we need? We need B. B is where it's at. And so we say, okay, can we replace what A is? Well, yeah, check this out. We can solve for A, but actually we can do something a little bit more clever. We can say, look, 1/4 A is 80. I need a 1/8 A. So we can say, oh, so 1/8 A is 40, right? Because just divide both sides by 2. You don't have to be clever, by the way. If you solve for A and say A is 320, that's wonderful. Now plug it in. So we get that 0 is equal to 10b. 1/8 A is 40 minus 100. Okay, 40 minus 100 is negative 60. Move it across. We get that 60 is 10 times b, or that b is 6. So now, we found b. Now, let's update our system of equations. Okay, now that we have it, we're almost done. So what do we have? So this 10b becomes 60, and all right, so we have x1 prime is equal to, and we're going to write things in the order, right? x1, and then x2, and then if we have anything else. So minus 1/4 x1 plus 1/5 x2. x2 prime, well, we have a 1/8 x1, a minus 1/4 x2, and a plus 60. So a couple of things. Where are our pieces coming from? So this part right here, this is our AX, And this part right here, this is going to be our non-homogeneous part. So when it says it's right as a non-homogeneous differential equation, it's coming from that piece right there. So, lo and behold, we can now write our answer, because it does say write it in matrix form. In fact, it even makes it bold. It's not just like, oh, you should write it in matrix form. It's like, write it in matrix form. You know, it's like very precise. Okay, so we have our final answer. Here we go. X prime equals, get our coefficients, minus 1/4, 1/5, 1/8, minus 1/4, times x plus 0.60. All right. And is this our answer? And why not? Other than the fact that there's a suspicious amount of space here. Well, remember, it says with the initial conditions. Okay, so initial conditions came from here. So our initial conditions is at x of 0. Our tank 1 had 700, so that goes in our first slot. And tank 2 was 120, which goes in our second slot. And there we go. Now we have our answers. Whew, what a fun problem. And, you know, it feels like a lot, but then you realize when you look at the page, oh yeah, half the page was the problem. So it only took half a page to solve it. And, but okay, all right, good. That was fun. I like a good mixing problem. But well, that means there's just one more left. All right, one to go. Let's finish it up. Number 6, our last problem. Using any valid method, find a particular solution xp for x prime equals 4 minus 2, 0 times x plus 0 minus 4t. So notice here, of course, this is a non-homogeneous. So sorry, all right, so non-homogeneous. There's really two different ways to approach this problem. If you can spell homogeneous, it's one of the hard things about the subject is all the spelling. And so our two approaches are variation of parameters, which kind of is a callback to first order linear differential equations, and undetermined coefficients. Now between the two, always go with undetermined coefficients if that's a choice. And so we'll check to see if that's the choice. So how do you check? Well, you look, you say, look at that non-homogeneous part. What are the functions involved? So in particular, when we stare at this, we say, well, really, it looks like t times this vector 0, -4. So the function is t. Now, we have a name for such a function. This, the technical term, is what we call nice. It's a nice function, which means undetermined coefficients is on the table. So we're going to go with that. Woohoo! Cool. All right. And before we get too far down our rabbit hole, and of course, you know, we are going to get a little far down here, let's make sure we have in mind what we're looking for. We're not after the general form. We're not after solving an initial value condition. We're after one single particular solution. So we're just after x sub p. So that's the good news. How do we get it? Well, if we're using the method of undetermined coefficient, the first thing we say is, what should a typical solution look like? We grab the functions involved. Now we see one function involved is t, because it's right there. And then we think back to what we talked about before, right? Where we talked about undetermined coefficients. And we said, oh, if you have powers, you got to go all the way down. So, for instance, if you have t, you also have to have all the lower powers, which includes 1. Say, okay, so we have t and we have 1. Those are our functions. Anything else? No, that's it. We're good. All right. Now, we have to check with the complementary solution. So that's why they gave it to us. They said, well, look, we just want you to focus purely on the particular solution. So we say, well, what are the functions involved? Well, we see an e to the 2t, and you really see an e to the 2t times t. there's no overlap. And so we say, aha, that's great for us. There's no overlap, which means that we don't have to do any bumping, because bumping can get annoying. So that says we really have a very good idea of what our particular solution looks like. So our particular solution looks like our first function times some unknown vector. We use AB, not the same AB here, but shh, don't tell anybody. Plus our second function times another unknown vector. Or if you like, it looks like A times T plus C, B times T plus D. All right, so that's our particular solution. Okay, good. Well, now that we have our particular solution, how do we find our A, B, C, D? Because we really don't have our particular solution. We have what our solution looks like. How do we actually nail it down and say, aha, this is what it is? Well, the answer is, no surprise, we have a solution. Plug it in. It was a great idea before. It's still a great idea. And so, all right, so we're going to plug our xp into our differential equation. So, start by taking the derivative. Well, that means take the derivative of both entries. All right, derivative of at plus c is a. Derivative of bt plus d is b. So this is our xp prime. All right, that's going to equal 4 minus 2 to 0 times our at plus c, bt plus d, and again this is our xp, plus 0 minus 4t. Okay, so now we're going to clean it up. In particular, we're just going to put all of that right-hand side into one vector. So let's do that. So that would be 4 times our at plus c. So we'll just do this slowly here so we don't make a mistake. Minus 2 times bt plus d plus 0. All right, and then we'll have 2 times at plus c plus 0 bt plus d and plus minus 4t. Okay, so we smooshed it all into a single expression, single vector, and let's do some grouping, because we like to group things together. And so we'll group things by either attached to t's or constants. So here attached to the t's we see the 4a and the minus 2b. So 4a minus 2b times t. Then for our constants we have 4c and minus 2d. And 0, which is 0. All right. Down here, well, attached to our t, we have a 2a and, 0. Okay, well, that's pretty easy. And a minus 4. Don't forget about that one. So we have a 2a minus 4t. What about our constants? Well, we have a 2c and a 0. And there is no constant. So plus 2c. And remember, this is all equal to a, b. Now what we do is we're going to match coefficients. So let's see what we have. Matching coefficients. We get the following. So what I mean is we're going to say, look, the coefficient for t has to match the coefficient for t. The constant has to match the constant. And same thing for the other entry. So the coefficient for t is 4a minus 2b equals, 0, because there is no t. So 4a minus 2b has to equal 0. Let's move this up a little bit so we have space. The constant 4c minus 2d has to match the constant. 4c minus 2d has to match a. 2a minus 4, 0t, right? Because there's no t. So 2a minus 4 equals 0. And then 2c, the constant, has to match the constant. 2c equals b. All right, so now we have 4 equations, 4 unknowns, and you're like, oh, this is going to take us a while. But probably not. Things tend to domino, right? So is there an easy one? I see an easy one. 2a minus 4 equals 0. Oh, that says a equals 2. Okay, that was not bad. Wait, I know a. Look at the top one. That involves a and something else. So if you look at it, that says 2b equals 4a, or b has to equal 2a. So if b equals 2a, that says b has to equal 4. But then come down here. 2 times c equals b. So 2c equals 4. So c equals 2. We've already got 3 down. Now here, there's a lot of stuff here, so let's just do it carefully. We're going to have here 8 minus 2d equals 2. Okay, because 4c is 8, a is 2. And, or if you like, that's the same as saying 2 times d has to equal 6. So d has to equal 3. So what does that tell us? It tells us our choices for a, b, c, and d. And so we can say that our particular solution, because we just need one, is a times t. So that's 2t plus b plus 4. And then c times, at plus c. It's easy to make mistakes. It's also easy to cross things out and fix it. So it's not a times t plus b, it's a times t plus c. All right, so be careful. So a times t plus c would be 2t plus 2. b times t plus d, well, that'd be 4 times t plus 3. And there we go. Good. Whew. All right. Problem done. Problem done. It even fits all on the screen at the same time. That's wonderful. Well, that was a good problem, and I hope you do well. I'll tell you that students generally like the second test. It's probably one of the more straightforward. It's very narrowly focused. And matrices aren't too bad once you get the hang of them. Finding eigenvalues and eigenvectors, students tend to do pretty great. The 2 problems that students struggled with on this test, number 6, but if you think about it, it has so many things in common with what we learned about when we taught it in just normal, ordinary differential equations without systems. Same ideas, you know. What are your functions? Is there overlap? What does your solution look like? Plug it in. Solve for your coefficients. It is the same process. The other problem they didn't like is the word problem on the mixing tanks. Those are so much fun. But that's all right. I hope you do well. I hope you found this practice useful, and I want you to go in, do great on the test, and just have a wonderful time. Well, thank you, and I hope to see you again. Bye.